Hello, this is FlippedHarber for Precalculus, and in this video we'll be covering section 4.6, Compound Interest. Our objectives for this lesson are to determine the future value of a lump sum of money, calculate the effective rates of return, determine the present values of a lump sum of money, and determine the time required to double or triple a lump sum of money. Now, this is going to be the first of several application sections in this chapter. Now, it's because of these application sections that I'm going to allow you to use a 3x5 card on the chapter test. So make sure that you get that filled out. I'm not going to give you a whole lot of time on the day of the test to get that filled out. Make sure you're ready. Make sure you're working on it now. Now, the outline for this video, we'll talk about simple interest, something that you're probably very familiar with. Then we'll talk about compounded interest, continuous compounding, and then we'll talk about present value and compounded present value. Now, simple interest is something that you should be well aware of. We use the equation interest equals principal times rate times time. And really the only thing that you need to make sure of is that your rate R and your time T agree. What I mean by that is if you're talking about a loan with a 5% per year rate, well, good luck finding one at 5%, but let's say you're talking about a loan at 5% per year. You need to make sure that whatever time you plug in for T is also in years. So if you're trying to figure out the interest paid after 24 months, well, you don't actually plug in 24. You'd plug in 2 so that it's the number of years, and that matches the interest rate. Now, if you want to know how much money is in an account or how much money is due on a loan using simple interest, you need to take the principal and then add that PRT. So this is what it looks like, is amount A, now that would be the amount in the account or the amount owed, is equal to principal times 1 plus RT. I just factored that principal out. Now I bring this up because we will be using this later in an example problem. Now, compounded interest is actually how the real world works. When you deposit money into a bank, you earn interest on that. When they pay you interest and then in the future again figure out the interest, they're paying you interest on interest. That's what compounded interest means. It means that your money grows faster than under a simple interest formula. Now, looking at the equation, A equals P times this quantity 1 plus R divided by N to the NT power. P is still principal. It's the amount that we're investing. It's the amount that we're borrowing, whatever. R is still rate. N is the number of times the interest is compounded. Okay? When we're talking about a loan, like a car loan or a house loan or a home improvement loan, whatever, generally banks charge that interest monthly. They compound it at the end of every month. But when you deposit money into a bank, they compound it only quarterly. That is 4 times a year. That would be after every 3 months they compound it. It's kind of a way to make money and not pay out a whole lot of money. But that N is the number of times that it's going to be compounded, typically in a year, because we usually plug in a number of years for our time T. Now, other options for compounding, you could compound monthly, so you would plug in 12 for N. You could compound weekly, that would be plugging in 52. You could compound daily, so you'd be plugging in 365 for N. The two most common are monthly and quarterly, though. All right, so I decided to actually pull up so you can see the difference here of what compounding actually does. These are actually interest rates for home loans, and you can see that they give you 2 different interest rates. They give you, let's say for example, a 30-year fixed rate on a home loan. They tell you that it's 3.375%. But then they tell you this other percentage rate, 3.546. Now the difference here is that 3.375 is compounded. But most people don't know how to compound interest. So they give us this other APR so that we could basically plug that interest rate in to our simple interest formula. So you can see that compounding is kind of like raising the interest rate because you're paying interest on interest, or you're earning interest on interest, a smaller percentage has a bigger effect. Okay, now, the absolute worst case scenario. If you went to somebody and they said, okay, we're not going to compound it daily, we're not going to compound it hourly, we're going to compound it continuously. Every single moment they compound the interest. This is what we refer to as continuous compounding. Now, what happens when you take n to be a, let me get rid of that. If you take n to be a ridiculously large number, 10,000, a million, as that n gets ridiculously large, what's inside the parentheses kind of turns into an e. So we say that continuous compounding is equal to principal times e to the RT. A lot of people just remember that because it's pert, just like the shampoo. So A equals pert. And again, it's like compounding every single moment of every day. Now, quite honestly, this is kind of a mathematical exercise. Banks do not pay, they do not charge with continuous compounding, but it's something that we talk about in math class, and specifically in this section. Now, the flip side of how much you owe into a loan that you're going to pay, or how much your bank account has in it, would be what we refer to as present value. And that's really just basically solving for the principal in the equation. And it looks so much similar because the way that we move that set of parentheses over is we just put a negative on the power. So you'll notice that it's the exact same equations as we had earlier. The A and the P are switched, and the power on the parentheses, or the power on the E, is now negative. So this is what we refer to as present value. Now, this would be useful if you wanted to know how much to deposit into an account so that in 5 years you have a certain amount of money. Okay, people actually do this when they're planning for their retirement. How much should I invest so that when I retire in 10 years, I'll have this much money? So that's what we refer to as present value, basically how much do I invest. Now let's do some example problems. It says find the amount from $10 invested, so they're telling us our p-value at 11%, that's our rate, compounded continuously, they're telling us which equation to use there, for a period of 2 years, and that's obviously our time. Now we're obviously going to use the A equals PERT equation, P e to the RT. We're going to plug in $10 for our interest. We're going to plug in 11% for our rate. But remember, when you plug in a percent, you have to change it into a decimal. So it becomes 0.11 when I actually plug it in for my rate. Now it's just calculator work. Type it into your calculator. You get $12.46. So if you invested $10 at 11%, after 2 years, you'd have $12.46 sitting there. Okay, so what if we invested $100 at 10% compounded continuously for a period of 2¼ years? Really, the only thing to pay attention to here is to make sure that you plug in the percentage and the time correctly. Our percentage we need to change to a decimal. Our time, well, 2¼ is 2.25. Type it into your calculator, and you'll have $125.23 at the end of that 2¼ years. Now, when we're doing these problems for homework, it doesn't make a whole lot of sense to round past the cent position. So make sure that you're always leaving 2 decimal places in your answer. This is money after all. So find the principal needed now to get $800 after 3½ years at 7% compounded monthly. So this is a problem where we're trying to find the present value. How much do I need to invest in order to have $800? Now I've switched equations because it's compounded monthly rather than continuously. So I need to make sure that I plug in 12 for n, that's in both spots, both in the bottom of that fraction and in the power. 3½ years is obviously 3.5. Now it's just a matter of typing it into your calculator. Make sure that you use the parentheses that you see on the screen, and make sure that you put the power in parentheses. So you would have to invest $626.61 in order to have that $800 3.5 years down the road. Now, here's a tough question actually. What interest rate compounded quarterly will give an effective interest rate of 7%? So if you think back to that table that I showed you, if we compound quarterly, we can act like it's simple interest if we get the rate correct. So what I'm going to do is I'm going to take my compounded interest statement, and I'm going to take my simple interest statement, and what I want to know is what interest rate do I use in the compounded side so that it's equal to 7% on the simple interest side. So I'm actually going to set these two things equal to each other. I've plugged in 4 for quarterly, plug that 4 in for n. I've plugged my 7% on the simple interest side, and obviously I can cancel out my p. Now you'll notice that the t is also gone. It's not that I canceled the t's. Those t's are in very different spots. It's not that I canceled them. I went ahead and I plugged a number in for them, because if we want to compare these two things, we've obviously got to have the same time. Well, what would be a really easy time to plug in? Well, how about 1? So basically I plugged in 1 year into both sides of this equation. You can see that I'm down to that one variable, r. So to solve for that r, just simple algebra to get this done, I would start with the 4th root, then I would subtract over 1, and then I would multiply by 4, and I get an interest rate of 6.82. So if I compound 6.82% quarterly, it's the same as a simple interest rate of 7%. Alright, if Angela has $100 to invest at 10% per annum, that's just a fancy way of saying yearly, compounded monthly, how long will it be before she has $175? So what we're going to solve for in our equation is time. Now, we know how much she's going to invest. We know the principal. We know how much money she wants to have. So we actually have our choice. We could use the compounded interest formula, or we could use the present value formula. It really doesn't matter. We're going to be solving for time, and it's going to be very, very similar in either way. I like to go ahead and use the one on the left just because that power is positive then. So I'm going to plug 175 in for A. I'm going to plug the 100 in for her principal. Our rate is 10%, but that gets plugged in as 0.10. And it's compounded monthly, so we plug in 12 for N. Now, our first thing that we should do is divide over the 100. And now that we've got a power to solve for, we just did this in the previous section, the way we're going to do that is with a logarithm. Now, what logarithm should I use? Well, I should probably use a logarithm that my calculator can use. Now, when I take the logarithm, that lets me move the 12t down front. So I have the natural log of 1.75. You could also use a log base 10. Just use something that your calculator can solve for. Bring that 12t down, so you have 12t, the natural log of the stuff in the parentheses. And now it's really just simple division. Divide over the 12 and divide over the natural log of 1 plus the fraction. And you find out that t equals 5.62. So it's going to take her a little over 5.5 years to earn that $75. If she waits a little longer, she's probably going to double her money. Okay, so that's it. We've taken a look at some equations. We've taken a look at some examples. You might want to get started on that 3x5 card for your test. You're going to have to turn that card into me with your test, but you might want to get started on that now. And it's time to get started on some homework. So I'll see you in class, and I'll see you online.